Final major phase of matter that we're going to talk about are gases. Gases are highly energetic molecules with neither a fixed shape nor a fixed volume. Gases will expand to fill any container that you put them in. A common example of gases are the gases which surround us and which we breathe. This is called the atmosphere of the Earth. If Earth's gravity were to turn off, atmospheric molecules would dissipate and disappear. Or if gravity acted but the molecules moved too slowly to form a gas, as might occur on a remote cold planet, our atmosphere would be a liquid or solid layer, just so much more matter lying on the ground. But our atmosphere is a happy compromise between energetic molecules that tend to fly away and gravity that holds them back. Without solar energy, air molecules would lie on Earth's surface the way popcorn settles at the bottom of a popper. This is also a problem that we have with terraforming other planets, which is where terraforming means making other planets more like Earth. Because different planets have different gravitational pulls and different temperatures, even if we were to pump the same gases in, they would either dissipate or fall to the ground, depending on the gravity and the energy in the air. The atmosphere also acts like a fluid and has certain amounts of pressure. However, unlike fluids in the case of mercury or water, which are fairly incompressible, which don't really change their concentration or their density as a value of different pressures, 50% of the atmosphere is below 5.6 kilometers, which is about half as tall as Mount Everest. 90% of the atmosphere is about 17 kilometers up, and 99% of the atmosphere is below about 28 kilometers. As you go up, you both have a change in temperature, a change in the density of the air, and a change in the pressure of the air. The biggest thing to talk about when we talk about gases is the ideal gas law. The more simple version of this is Boyle's law, which states that at a constant temperature, pressure times the volume of a gas is constant. Non-constant pressure, however, the pressure times the volume of a container is equal to the number of molecules in the container times the temperature T times a constant which converts temperature to joules or whatever unit of energy we want to, called the Boltzmann constant. Air also has a buoyant force in the same way that liquid does, in that an object surrounded by air is buoyed up by a force equal to the weight of the air displaced. So for a gas-filled balloon, it will only rise as long as it displaces a weight of air greater than its own weight. Because air becomes less dense with altitude, a lesser weight of air is displaced per given volume as the balloon rises. Since most balloons expand as they rise, their buoyancy stays fairly constant until they can't expand anymore. In this case, the air pressure goes down as the volume goes up until the volume can no longer go up, in which case the balloon will stop rising because it can no longer expand to be pushed up by the buoyant force. Another principle that is usually talked about with fluids, and remember that air is a type of fluid, is Bernoulli's principle, which states that where the speed of a fluid increases, the internal pressure of the fluid decreases. This is also similar to a continuity equation, which states that any number of molecules which enter an area must leave the area. Because the particles are moving faster through an area, in order to keep the number of particles moving through the area constant, the internal pressure, which is related to the number of particles per volume, is going to become lower. This also means that the cross-sectional area of a pipe times the velocity of the fluid moving through the area at that point is going to be constant. A major use in Bernoulli's principle is creating lift for airplanes, where the top of an airplane wing is going to be a longer flight path than the bottom of the airplane ring. By continuity, the number of particles moving over the top and below the bottom have to be equal to each other. However, because the particles on the top have to cover a longer distance over the same amount of time, they're going to have a higher velocity, which means they have a lower pressure, which means that there is going to be a higher pressure on the bottom of the wing versus a lower pressure on the top of the wing. It's going to cause the wing to be lifted up with a net force. Bernoulli's principle also explains why trucks that pass closely on the highway are drawn towards each other and why passing ships run the risk of a sideways collision. Water which flows between the ships travels faster than water that flows past the other outer sides. Streamlines are closer together between the ships than outside, so the water pressure that acts against the hulls is reduced between the ships. Even a slight reduction of pressure against the relatively huge surface area at the sides of the ships can produce significant force. Unless the ships are steered to compensate for this, the greater pressure against the outsides of the ships forces them together. Finally, we are going to talk about a fourth state of matter, plasma. There are several states of matter beyond the elementary liquid, gas, and solid, but the matter that makes up most of the universe is actually plasma. A plasma is an electrified gas. The atoms that make it up are ionized, stripped of one or more electrons, with a corresponding number of free electrons. In addition to making up most of the matter in the universe and making up most of the matter in suns and stars, the neon gas in an advertising sign becomes a plasma when its atoms are ionized by electron bombardment. Neon atoms, after being activated by electric current, emit predominantly red light. The different colors seen in these signs correspond to plasmas made up of different kinds of atoms. Argon, for example, glows blue and helium glows pink. Flat plasma TV screens, which I think are less prominent than they were when this book came out, are made up of thousands of pixels, each of which is composed of three separate subpixel cells. One cell has a phosphor that fluoresces red, another green, and another blue. These pixels are sandwiched in a network of electrodes that are changed thousands of times in a small fraction of a second, producing electric currents that flow through gases in the cell. As in a fluorescent light, the gases convert to glowing plasmas that release ultraviolet light that stimulates the phosphors. The image on the screen is the blend of pixel colors activated by the TV control signal.